pleasure to be here. So I guess the good news is that, you know, you are nearing kind of the end of the summer school, and I've heard that you were taught everything. So I can just, you know, do a 3 hours and question and answer session if you want. So, so my plan was to basically give an introduction to the quantum simulators and computers based on neutral atom arrays. But I mean, again, people have talked about it, so actually I could possibly even, you know, okay, I will start this, and you know, we'll see how it's going. And so I have some options for the second part of my lecture. So, okay, so, but kind of at the high level, this work and a lot of the other things that you have heard is really part of the quest for controlling quantum world. And in this quest, what we as scientists are trying to do is to isolate and control simple quantum objects and build more and more complex systems from them. And what we would like to do is study new physics with this kind of engineered quantum systems, but also start exploring new applications. And you basically hear about these things, you know, maybe now almost too much. So in fact, you know, the last 2 days I'm hearing even more. And it's actually sometimes a wise thing to step back and kind of, you know, think a little bit where the field is this. So at the moment. So, and actually in that spirit, you know, there are 2 big challenges that this field is facing, which are really open scientific frontiers. And one of them is how to build large-scale quantum systems. So there is a progress being made across many platforms, but I think it is at the moment unclear if truly large-scale quantum computer can be realized and how, and in particular when, right? So in particular, as you read your, you know, Twitter feed or X feed now, you know, bear this in mind, you know, because, you know, like, you know, this, for example, recent announcement presents a roadmap to build a quantum computer based on quasi-particle, which, you know, so, but anyway, so you get my point here. So, and the second, but okay, it's an exciting frontier, you know, building topological quantum computer is an exciting frontier as well, you know. So, and the second problem is that, you know, even if I were to kind of, you know, bring here a quantum computer, you know, okay, you guys are kind of, you know, advanced bunch. You probably know what to do with that, but in reality, there are very few applications known that quantum computer can do. So, and that's a second challenge, how to apply these machines to achieve useful quantum advantage. So, but the field is now at the exciting point in that there are several platforms where, you know, now dozens or hundreds of qubits are being kind of realized. And the biggest challenge that this field is facing is to address kind of contradictory requirements of what I would call controllability and scalability. So, and this challenge is kind of fundamental because basically all objects around us are built from quantum particles. Yet, I mean, there is nothing quantum about this table, right? So typically when the object becomes big, you know, it becomes completely classical, right? And so when we build quantum computer, you know, we are trying to really, you know, like, you know, force nature into something which it does not like to do. You would like to have a big object and, you know, like with many qubits and then very complex superposition. And that's the challenge which this field is trying to address. So the current frontier, there are, as I said, there are some systems which are sort of approaching or exceeding 100 qubit scale. And with them, one could actually try to do tasks which modern classical computers have hard time doing. But in addition, what we can do is use the systems to learn how to build bigger and better quantum machines, and also start addressing this application challenge, explore kind of useful algorithms and scientific applications. So in that sense, this is now like in the field is in the age of like scientific discovery, right? So just before for in any field, before you sort of start, you know, rolling out products, I mean, you have to go through discovery and, you know, the stage, and that's where this field is, and it's actually very exciting. So okay, so in these lectures, you know, my original plan before I learned that you had already multiple kind of talks about this was to talk about three things. One is talk about introduction to neutral atom quantum computing. I think you've heard already a lot from Harry, so I will actually now check how well he lectured by asking you questions. So, and then I thought about talking about two directions. One is addressing the so-called quantum error correction frontier. Another one is quantum simulation. So let's see how far we will go. And I think in these kind of lectures, usually the goal is to cover more in depth than rather to cover more. So I encourage questions. And in fact, I'm wondering if you guys have any questions about any remarks that I've made before. Okay, well, I did not communicate too much, so that's okay. Otherwise, I will start asking you questions. Okay, so right, so I will talk at least in the first part of the lecture, you know, depending on how things will develop, or maybe the entire lecture about quantum processors based on cold neutral atoms. And there are multiple reasons to consider them as a good qubit candidates. So these systems have excellent coherence properties. So, for example, probably the most precise measurement instrument created by the humankind is optical atomic clocks, which actually utilizes neutral atoms. And it's actually easy to create large numbers of neutral atoms. Moreover, neutral atoms strongly coupled to light. That's something which also will come later in the talk, will be important. But there are also drawbacks. In particular, atoms generally interact weakly with each other, and neutral atoms are hard to control, in particular individually, in particular in large numbers. So, and this control issue I would like to kind of, you know, emphasize again. So here is an image of kind of typical magneto-optical trap. So it contains around 10 million, this specific image of nearly motionless atoms. So basically, if you were able to kind of grab individually and control each of the atoms, it will directly give you about 10 million qubits, which actually is a significant number. So, so what it really means, and actually if 10 million is not enough, you can create a bigger cloud. So what it really means is that the cold identical neutral atom source is essentially unlimited. So, and the key challenge is to control them classically. So just before we go into the details, I want to kind of step back and give you a little bit of a summary in one slide of atomic physics, which you need to know. So, so we in these lectures focus on hydrogen-like alkali atoms, which have a single electron which orbits around the nucleus. And this is, of course, a classic quantum mechanics problem, so you can solve it. And there is this hierarchy of energy levels. So one of like the kind of, you know, one part of hierarchy is the kind of larger scale is the one which is determined by the so-called principal quantum numbers. So there's infinite number of these levels, and most important, they are anharmonic. So why is anharmonicity important? So you guys talked about, I guess you talked about qubits already, right? So what system can be used as a qubit? What? What? Well, you're well educated, yes, yeah. But okay, yes, I think this is one of the that might be it. You know, you might not need to know anything more than we, but exactly. So for that reason, I mean, basically almost kind of like atoms, they have anharmonic spectrum, right? They can be used as qubits, you know. Molecules have anharmonic spectra, they can be used as qubits. So, but there are some systems like photons, for example, right? They have harmonic spectrum, right? So, and even though you can potentially, for example, you can use photon polarization to encode qubit or some kind of other time beam encoding, because it's a harmonic oscillator. This, you know, you cannot just ignore all of these other energy levels. So it's actually why building quantum computers from photons is actually very hard, you know. See, this reminds me if I want to say something which is not public, it's someone else. So I'll stop on this. Okay, but so basically this okay, so apart from this kind of principle, what's called Rydberg series, there are other sublevels, and in particular, even the simple hydrogen-like atom has both electronic and nuclear spins, and these electronic and nuclear spins kind of results in kind of splitting of these levels. So this results in fine structure, hyperfine structure, and basically we can utilize all of these kind of sublevels for different purposes. So in particular, for encoding and storing quantum information, we will typically use spin sublevels associated with the ground state of indeed rubidium-87 atom, as was correctly pointed out. But it turns out that for some other purposes, for example, to make atoms interact, you actually need to excite atoms, for example, in some of these Rydberg states. So okay, so this would be kind of a basic building blocks of this approach. And then, of course, what we need to do is we need to first, kind of isolate and localize single atoms in space. And for that, we will use focus beams of light, which actually are called optical tweezers. The idea is the following. So basically, these focus beams of light project some force into atoms. And essentially, you can think about atoms as a kind of small dielectric objects, which can be polarized by this kind of light beam. And as a result, this kind of little dipoles, they attract to the point of either highest or lowest laser intensity. And and that depends on actually sign of polarizability. It actually depends on the sign of the laser detuning from nearby level. And so, and in this kind of approach, basically what happens is that this focused light beam creates the so-called dipole trap. And this depth of this dipole trap is typically kind of, some, maybe, kind of hundreds of microkelvin or some kind of millikelvin. So what it means is that to load this trap, you need to actually slow the atom down, and this is typically done by using laser cooling techniques, by basically buffing atoms in the combination of some laser beams of certain color. You can really slow the atom such that it actually can be grabbed by this trap. And so basically the way how most of these systems work is that you don't, in the modern days, you don't start with just one tweezer, but you start with by now thousands of tweezers, and you try to basically load them all at the same time. And often, if you try to do it, this loading is not perfect. So actually, in most of the cases, loading is something like 50%. What you do, so basically what it means that the system has like classical entropy. So to get rid of the entropy, what you can literally do is basically take a picture of atoms and figure out which traps are full and which are empty, and basically eliminate the empty traps and kind of move the atoms, in the full traps around to create basically an desired array of atoms. So with that, typically you end up with the system where atoms are sitting a couple of micrometers from each other. So at this point, the system is completely classical. There is no interaction. The interaction between the atoms is negligible. And to make them interact, you need to do something. And actually what we'll be doing is exciting them into the Rydberg states. And that's the basis. That's the foundation of this approach. All right, so Rydberg states, again, kind of crash course, are this kind of, special states of atoms where electron is very loosely bound to the nucleus. So, and as a result, these atoms in the states have kind of very exaggerated properties. So, for example, like if you pick, some principal quantum number on the order of 100, so then the effective radius of orbit, which scales as n squared, will be actually a fraction of the micrometer. Such an orbit can be very easily polarized if you apply electric field. And in particular, what it means is that if you have two atoms near each other, they will actually kind of modify, they weakly perturb, basically an orbit of each other. This will result in a very strong interaction. So in fact, the van der Waal interaction between the atoms in n equals 100 is 14 orders of magnitude stronger than the van der Waal interaction between ground state atoms. So 14 orders of magnitude is actually a big number, and one can make good use of that. So in addition to this, these Rydberg states also have long lifetimes, hundreds of microseconds. And these combination of a strong interaction and long lifetimes can be put to good use. And the specific approach, which kind of most of the modern experiments utilize, involve so-called Rydberg blockade. And so let me explain this to you. So what it is that if you take a pair of atoms and excite them from the ground state to the Rydberg state with resonant light beams, then if the atoms are very far away, then they're basically, they won't interact. So they just undergo independent Rabi oscillations. However, if you start bringing these atoms together, eventually this interaction will take over. And what it means, if you still try to excite atoms resonantly, you will be able to excite one atom or another, but never both. So the simultaneous excitation is blocked at distances smaller than the Rydberg blockade radius. And actually it turns out that this kind of simple mechanism is a very good, very robust mechanism to entangle atoms and do quantum logic. And the reason is that it is actually insensitive to exact position between the atoms, and it's insensitive to motion of the atoms. So in a way, this Rydberg blockade makes this interaction between atoms almost digital. So atoms either don't interact, if they're far away, or we are close to each other. The interaction is almost infinity to the leading order. So it basically, its kind of interaction is either on or off. And basically, the combination of this kind of atom array, this Rydberg, can be used to build quantum processors. So basically, in what follows, the experiments I will show you involve essentially creating some registers of atoms, some arrays of atoms. And then, by shining, light on the atoms of different colors, we either would change the spin state, or excite them to Rydberg states, and then after, then this constitutes quantum logic. And then after this, quantum logic operations, eventually you need to again read out the atoms. But in this case, what we'll do atom images in a state-dependent way. If the atom is in one state, it will appear as bright, and another one is dark, and it constitutes a projective measure. And so this this combination of ideas now kind of resulted in an exploding field. There are a couple of hundred of experiments, being kind of built around the world, and actually at least 12 companies are trying to commercialize this technology. And the kind of real opportunity here is that with these basic ingredients, you can really innovate. You can use different types of atoms. you can combine, for example, tweezers with optical lattices. You can also apply these techniques to a molecular array. So these are some pictures of some kind of exotic atoms. So these are two-species array from Hannes Bernian lab then in Chicago. This is actually a picture of over 5,000 trapped cesium atoms in Manu Lander's group at Caltech, and this is actually an array of 2,000 sorted atoms in Javier Penn's lab and USTC. And this is really an exciting frontier, because it bridges this kind of quantum computing with many-body dynamics, quantum metrology, and as I already mentioned, complementary to optical lattices. So okay, so that's kind of the basic approach. So and to leading order, these experiments share this kind of philosophy, but of course, like the devil is in the details, and so, for example, as already mentioned, you can now think about picking a certain atom. So, for example, rubidium-87, as was already indicated, is a very good choice. It's actually for multiple reasons, and we can discuss why. But there are also a few experiments now utilizing these alkaline earth atoms like ytterbium and strontium. But even within an atom, you can actually have different types of encodings. And so, for example, I mentioned, that, spin states is a natural way to encode, but you can also choose instead encoding between kind of ground and Rydberg atoms, and this in particular is often used for analog evolution. So likewise, in alkaline earth atoms, you can think about ground state spin, metastable spin, you can think about optical qubit and also a ground Rydberg. So in addition, of course, you have these other transitions in atoms, and they're typically used for atom cooling, state rotation, and detection. So there are many opportunities, and I think these opportunities actually are now starting to being exploited, and depending on application, depending on what you want to do. So okay, just kind of a simple example of how we can use this Rydberg interaction to entangle atoms, Rydberg blockade. So suppose you just have two atoms, one pair of atoms, and you just excite them both to the Rydberg state. So in this case, this is indeed now focused on rubidium-97, and basically exciting into the N, kind of somewhere, between 50 and 100. And in order to do it, you need to use two colors of light. So in this case, it's a will be a blue light, exciting atoms from into like a P state, and then eventually using the infrared light exciting the atoms into a Rydberg state. And so if these atoms are under blockade, then it's very easy to understand what will happen. So in this case, you will be able to excite one atom, but not two. But actually, if you excite both atoms at the same time, you will not be able to kind of distinguish whether you excite one atom or another. So in fact, what you will do, you will excite this kind of coherent superposition of the atoms, and note that doubly excited state now is completely shifted away from resonance. So in fact, you can see it in the experimental data. So here, this is the probability to excite two atoms. There is actually 0. So, and this atom pair oscillates between being in a ground state and being in a first excited state. And to actually check that you indeed apply coherent superposition, what you can do, you can just imprint a small phase shift here, differential phase shift, by just applying a different laser beam. And by looking at this kind of, oscillations between these two states, you can actually really verify that this thing is phase coherent. And you can, this is actually still the data, early data, 7 years ago. So at the time, it was, like, it was relatively high fidelity of entanglement, but by now it's, one can entangle with kind of nearly 3 nines, and also, very, very quickly. So, okay, so this kind of, that's a basic ingredients of this kind of Rydberg system. Maybe let me see if there are let me pause it and see if there are some questions.
So just to extend the question on photons, using photons as qubits.
Yes.
Can we use the nonlinear interaction of photons with a highly nonlinear medium down to a few photon level to create an harmonicity?
Yeah. So this is okay. So yeah, indeed, like photons, historically, people first thought about photons as qubits, and then they realized that it's, like while it's good to use photons for communication, for computing, it's hard because they don't interact. So, you can indeed kind of, address this challenge. For example, by coupling photons to the linear medium, which is extremely nonlinear. So, for example, if you take a cloud of Rydberg atoms, you can make it extremely nonlinear. In fact, nonlinearities at a single photon level has been implemented. The issue is that, if you want to use this nonlinearity to do quantum logic, you have to also make sure that things like losses are very, very small. And this photon loss is actually a big problem because it's very hard, like you have a lot of modes of light where the light can scatter. So, you can realize, and indeed there were experiments both in Rydberg atoms, but also if you couple photons to single atoms in cavities, you can also implement nonlinearity. And you can even make, like deterministic gates between photons. But I would say, like at least at the moment, the losses are way too high to do anything scale. There is another approach, which also people realized maybe over 20 years ago, and you can actually use measurements to do quantum logic and linear optics. The problem, however, and this is what, there is a community of researchers exemplified by another company in the news, PsiQuantum, which actually tries to build a quantum computer. Kind of from that, the problem here is that you essentially, if you only use measurements, you kind of outsource all of your overhead in terms of doing, initializing qubits, doing logic goes into measurements. And then this problem of loss becomes actually even more severe. And whereas theoretically both of these approaches could be used, in practice it really it seems daunting. And honestly, I mean, this measurement-based approach sort of was viewed as kind of easy approach. I wouldn't even say that that's the case. So, and I think the fundamental issue is you need to kind of address this combination of loss and nonlinearity. I mean, that's a kind of. But photons will almost certainly play an important role for communication, right? So, any other questions? All right. So then, what I will do, I will kind of first, kind of go on and show you how one can utilize, these ingredients to do quantum simulations. And this actually literally implements, kind of almost word to word the original idea of Feynman. So if you read some of his early papers, he was thinking about like string of atoms, and they, turn interaction between them and kind of, evolve and read them out. So actually, the simplest example of that is, suppose you have a string of atoms, and now let's use ground Rydberg encoding. And so if you write down the Hamiltonian, which describes this chain, it will have several terms. It will have this kind of Rabi oscillation term. It will have a detuning term, and the number of atoms, Rydberg atoms on each side, and it will have the interaction term. But actually, if viewed written in this way, this Hamiltonian is actually corresponds to Ising type model, and you can ask the question, for example, what's the ground state of this Hamiltonian? And this ground state can be characterized by two axes. One is a detuning axis, and another one is kind of this kind of interaction range And if there are no interactions between atoms, the ground state is solely determined by the detuning. So if detuning is negative, you want all n's to be 0. Basically, all atoms should be in the ground state. If detuning is positive, then to minimize this Hamiltonian, n should be 1. So all atoms should be in the Rydberg state. But of course, once you turn on the interaction, so for example, if nearest neighbor is blockaded, you will not be able to reach this state. So what this means is that, if you turn the interactions such that you have nearest neighbor blockade, then basically the ground state, will be every other atom, will be in the Rydberg state. And this kind of, excitation will alternate. So basically what you see here is that this system is ordered. So it's actually kind of anti-ferromagnetic or Niel ordering. This constitutes, basically, the state breaks Z2 symmetry. So if we extend the range of blockade even more, then, every third atom only can be excited, so in this case, you will have Z3 ordering, and then this kind of thing continues. And you can now explore this phase diagram by basically starting with all atoms in the ground state and just, changing adiabatically, adjusting the interaction, and then just changing adiabatically detuning, going from negative to positive, and in this case, you can immediately see that, this chain, indeed orders. So this is up, down, up, down, up, down ordering, is up, down, down, up, down, down ordering, etc. And moreover, what you see is a kind of, if you stop at different places as a function of detuning, you see here that, the system is all atoms in the ground state. Here there is this order, and in between there is this kind of, fluctuating, pattern. And these fluctuations is really a signature of a phase transition. The system goes, from one state to another, and in between undergoes the quantum phase transition. And actually, in this case, by just programming this interaction, you can really explore these different symmetry breaking, these different transitions actually have different nature, so you can study them, you can study some various kind of properties and so on. So so this is an example in one dimension. So the modern experiments are all include two-dimensional systems, and they are powered by this device, which is called special light modulator. It's actually like a computer-generated hologram. It's actually something of this type is what we use in this projector to project the slides. And so basically, by programming this hologram, you can just deflect this light in different directions. And in fact, by programming the right type of hologram, you can actually create the pattern, two-dimensional pattern of this, traps of this tweezer arrays. And if you project them into this vacuum chamber, you can have, easily, thousands or actually tens of thousands of these spots where you can trap atoms. So the only drawback of this SLM is it actually is relatively slow. So to circumvent it, we actually use a separate channel in which we create a separate set of tweezers by using two acousto-optic deflectors. Acousto-optic deflector is a device where actually you inject a sound wave in a crystal and it deflects the light. It's actually similar, like if you have seen these barcode scanners in supermarket, they often use these acousto-optic deflectors. And so, but actually it turns out that you can, use it to really generate this dynamically movable kind of tweezers. And in this case, we use two of them to move both rows and columns independently of atoms. It's all, of course, computer controlled. So these are already kind of, fairly old kind of images where we start with 600 traps and create, array of about 300 atoms, by sorting them out. So these are these kind of excess atoms. And so in this case, basically we have filling, typically over 99%. So kind of modern experiments, 3/9 of filling is typically achievable. And so with that, one can create different types of arrangements and even arbitrary patterns. For example, these are places where you want to put atoms, and here are the actual atoms. And one can now use this two-dimensional system also as an analog quantum simulator, very similar to what I've showed you in 1D. So here, for example, we start with the 2D square lattice array and shine light with the kind of negative detuning, and then adjust the spacing such that nearest neighbor is only blockaded. And if we now basically do this kind of detuning sweep from negative to positive, here we create an anti-ferromagnetic state where every other atom is excited, and this is basically a perfect anti-ferromagnetic kind of pattern. So, like, by looking at this image, it is of course perfectly ordered. So it's not every, if you do the experiment, not every shot is actually like this. So you have typically some defects, and so you can characterize it by looking at things like correlations. So it's a second order correlation, density correlation function. You can also look at things microscopically. So, for example, turns out that states like this, even though they are most probable, compared to all other states, it's still kind of exponentially, the probability to observe it is exponentially small. And in fact, it decreases with the system size for multiple reasons, both technical, but also fundamental, like, for example, quantum fluctuations. But you can also, what you can also do, you can not just study the statics, but you can also study dynamics. And for example, what you can do, you can actually study things like correlation growth by just going across this phase transition with variable speed and looking at how the effective correlation length grows as the size of the speed. And actually, we can use this type of observation to study the nature of this phase transition. In fact, turns out that this phase transition is actually a second order phase transition, and there are some kind of universal properties which one can extract, and these universal properties are characterized by something which is called critical exponents. It's basically how correlations grow, and basically by collapsing this data with just two parameters here, you can actually really bring all of these curves on the top of each other. And so basically this type of experiments really allow us to study these phase transitions in great detail. And in fact, this involved this data already a few years old. Just last week in Nature, there are new results kind of studying more details of these phase transitions, in particular things like coarsening dynamics, basically, bringing the system to certain point in the parameter space and just letting it, and we can look how, for example, how the domains grow, how they evolve, and there is also, we observe something in the analog of the Higgs mode. So yeah, so this is an exciting frontier, and in fact, over last couple of years, we had actually a lot of fun, exploring different elements of that. So as I already mentioned, we studied this 2D phases. We also studied dynamics. We explored topological properties, actually built a kind of baby version topological qubit, and also studied things like combinatorial optimization. So in fact, I think Harry talked to you about the square machines on the cloud, where one can actually do experiments now, from remotely. So I think this still remains a kind of a very exciting frontier. But what I really want to focus this lecture is on this kind of more on a digital evolution, and using it to explore both digital simulations and quantum error correction frontier. But maybe it's a good time here to stop for questions. So any questions about this analog side? Yes.
When you said Time, is that for T1 and T2 coherence time?
Sorry, what? Can you repeat it?
When you said 100 milliseconds for the coherence times, was that for T1 and T2 coherence time?
Okay, so there are different coherence types associated with different levels here. So I will talk about in what follows. I'll talk about coherence times associated with encoding spin qubits, and these coherence types are typically seconds. So I mean, it can be many seconds. So for the but for Rydberg states, the typical lifetimes are maybe in coherence times are in sort of tens or maybe hundreds of microseconds. So in fact, the lifetime of the Rydberg state is, I think, the Rydberg states which we use is typically in a kind of 100 microseconds range. The coherence times are typically somewhat shorter, maybe tens, of microseconds. So that's why, for example, if you do this if you involve this ground Rydberg in, encoding, the evolution time will be typically limited, And what you will see if you use ground Rydberg, use spin encoding, if you will use basically ground state encoding, Rydberg state will be needed to do the gate, but then the approach will be to excite into Rydberg state and de-excite as fast as possible. Any other questions? Yeah.
C2 ordering of qubits through the blockade. Can each subset of qubits, can you adjust your blockade to isolate each subset of qubits from the initial entire set? So like 1, 3, 5, 7, and then those are isolated, and then you can swap to 2, 4, 6, 8.
So your question, you're asking, can you by hand initialize a state like this?
Well, can that state be initialized and then swapped for the other set of qubits that were initially blocked?
Maybe that I don't completely understand. So you are thinking about 1D or any? One dimension, 2 dimension. I see. So yeah, so sorry, now I have to watch for was a mistake to go. So so maybe I still don't completely understand. So it's easy to initialize atoms all in a ground state. You can also initialize atoms in some kind of pattern of the ground and excited state. And the way how you do it, you basically, for example, you can detune some of the atoms, right, and then excite the rest. So but so what's the swap idea? So what will
I see it. It was a misunderstanding on my end. I was so that the initialization provides the every other physical qubit. And I was
okay, so here, so here we're talking about kind of ground and excited state forming the qubit. So in a way, it's kind of a funny qubit because, for example, like if the 2 atoms are nearby, you cannot have both of the atoms with blockade. You cannot have both of the atoms excited. So your sort of space is somewhat limited, right? But I mean, other than this blockade constraint, in principle, you can initialize any state that you want, and then you can let it evolve, So of course, maybe you are thinking about some kind of further things, Maybe you can, if you use some other additional auxiliary levels like hyperfine levels, you can create ground Rydberg superposition and then store it in ground Rydberg superposition, and then you can do swap and stuff like that, in this case. Yeah.
systems, like we do not consider the spontaneous emission of the atoms?
Yeah, it is, yes. And I mean, like in this case, of course, you don't want spontaneous emission. But the spontaneous emission can play a role. And there are two types of spontaneous emission kind of events. So one, the actual excitation scheme here is that you go from ground state, S state, and B state, and then eventually to this kind of and S state, Rydberg state. And so basically, we have two types of spontaneous emission. One is the decay from the state, and another one is the decay from the S state. So typically we use two layers, and this transition is all present. So the spontaneous emission is suppressed. Now, the emission from this state results in this kind of 100 microsecond coherence time. So, and usually try to do things, much faster than that. And so basically, for example, but with some small effects from that remain. So, for example, with small probability of this decreasing probability of creating perfect pattern here is in part due to these effects of decoherence and spontaneous emission. So I should say, and this will become more important in the future, is that this effect of spontaneous emission here, particularly from this state, can be actually quite non-trivial. And the reason is, so if the atom decays from the state, it decays with substantial probability to other Rydberg states, for example, m minus 1. It can also go to n plus 1 because of blackbody rotation. And the problem about these states is that, okay, so they're sort of injected, if you want, from a computational substrate, but they still there is like manifold. These states like this can still interact with other atoms. And the effect of this kind of state can be actually very damaging if you don't handle them properly. This is that we would, when we'll talk about error correction, we actually maybe can discuss about that. So these type of atoms you really don't want to have in your system. And actually, in reality, again, just maybe jumping ahead. So the way how we typically do this excitation into the Rydberg states, we turn off the traps and just excite them into the Rydberg states and then de-excite them back. And then turn the traps back on. And so what happens is that these atoms actually are undertrapped. So if you turn traps back on and wait for a while, so the atoms will be completely ejected. So this will correspond to the so-called atom loss error, which can turn and convert it into some ratio error. I don't know if Terry talked about it. So it's actually it's an error mechanism, which in principle can be very damaging, but if handled correctly, it can be extremely advantageous because ratio error is actually like very favorable kind of to correct. So. Any other questions?
So just for clarification, we see that we kind of lose the correlations as we go towards the edges. Is it because of the edge effects?
Well, yeah, so it's also a very good observation. So in fact, so here, okay, I mean, on this plot, these correlations basically extend almost across the entire array. And so basically this faded connection is essentially connected to the system size. However, the edge effects in such systems can be quite non-trivial. And in fact, in some of the kind of more complex, experiments for some of the more complex phases, which we studied, you can literally see that correlations often start to grow on the edges and grow inwards. And in fact, for some of these phases, the bulk transitions can be first order, whereas the edge transitions are second order. And what it really means is that this edge kind of results in kind of nucleation of this growth. And so this is connected also a little bit to this coarsening dynamics. I mean, how does crystallophytes grow, right? I mean, it's not, usually you have some small grains and then they start kind of growing around. I mean, it's a little bit similar if one can really study quantum, physics. So I could give easily 2 or 3 hours of lectures about this. And this actually, for example, the most recent Nature paper really studies this quantitatively. And there is a difference between, for example, quantum coarsening and classical coarsening. And likewise with these edges, there is a difference between quantum phase transitions and classical phase transitions.
You can possibly study effects where only the corners are correlated and not the.
Exactly. So in fact, so for some of the phases, so in this 2D system, it has actually quite complex phase diagram. Let me see if I have some. Maybe this slide. So it's the example of the phase here. If you look at that, so this one, so in this is like a phase with slightly larger blockade radius. And what you see is this ordering is no longer a square, is no longer antiferromagnetic. So there is this kind of, very funny kind of ordering pattern here in the bulk, which is, where this, like this line kind of guides you a little bit. But look, for example, look at the edge. The edge is almost perfectly antiferromagnetic. So this is an example where the edge orders first, right? And it kind of drives inwards. So it's actually quite intricate. There is quite a bit of literature now. And then one can really study effects of this type. Yeah.
Do you guys explore resonant Rydberg interactions on your system, or is it kind of worth the increased interaction strength, or the blockade's a good kind of balance?
So the question here is basically the following. So if you wanted to, for example, maximize the speed of the interactions, so what you would do, you would essentially try to do the following. So you try. Get about this visual stage, you will just have basically bound. Okay. And so usually what we do, we kind of excite these atoms with the triangle frequency, which is typically like few megahertz, right? But when the atoms are close to each other, this Rydberg blockade interaction, can be like a fraction of gigahertz. So it's frequency is much smaller than this interaction. That's what corresponds to the Rydberg blockade approximation. But you could say, well, if you want to do it really super fast, what you can just blast your atoms with light and try to go up and down as fast as possible. You will not be in a blockade. The interaction then will be limited by this kind of one-on-one interaction between the atoms, which depending on levels and so on, can be easily few gigahertz. So in principle, as we'll discuss in a second, doing Rydberg gates fast is the faster you read, the better. The better off you are. However, this blockade approximation allows us to be extremely forgiving in terms of, for example, like temperature of that. So we do not work with atoms in emotional ground states. it allows us to be extremely forgiving in terms of also position fluctuations, and more of this kind of digital character, will be kind of very important, particularly if we want to do gates in parallel. So I would say, this current generation of experiments or what's going on is we feel would be impossible to treat with blockade. And that being said, if we really start pushing, and you'll see that, sort of the gate fidelity is now approaching 3 nines, there is, I would say, very clear path to 3 nines. If we start pushing to 4 nines, maybe 5 nines, maybe that approaches can be explored. But this will come, with problems, and actually, in addition to the fact that in this case, you basically will be very sensitive to exactly how your position atoms. In addition, in this case, there will be a force acting on atoms which is state dependent. So the state dependent force will actually result in entanglement between internal degrees of freedom and multiple degrees of freedom. And this actually also can be quite damaging. Again, if you do it super fast and really small, but okay, that's I think this, I would say this should definitely be studied, but it's not clear to what extent this. Other questions? Or should I ask you a question? So this, okay, let me ask one question. So, the Rydberg kind of interaction is clearly the central part of the physical implementation here. So this van der Waal interaction in particular, which we use, scales as n to the 11th power. This 11th power is kind of intense, so the question is, where does it come from? So the size of the Rydberg orbit scales as n squared. Okay, it's sort of, from quantum mechanics 101. But like, how does it end up to the 11th power?
Second order partition. So like if you look at the difference in energy levels, it goes like n cubed. Then in second order becomes n to the power 6.
Whoa.
No, but then cube and then.
Wait. I already forget more than that. Okay, so at this time, so at this time, we need to do perturbation theory. But perturbation theory is what? So we're looking at van der Waal. So direction. It's a second order of perturbation theory. What?
The dipole interaction.
In a dipole interaction. Okay, so first off, there is a dipole interaction, right? Dipole interaction scales like a dipole moment. Dipole moment scales like a size of the atom of R cubed. Also n squared. Okay. It's remarkable. You almost do the answer, but no. The dipole moment is here. This is correct. Dipole interaction. Sometimes so it's actually dipole moment squared, right? There are 2, right? So it's actually a squared. So this gives rise to n to the 4th. over cubed. But it is in, but like, where does it come, right? So, at this point, if you have two atoms with unharmonic spectrum of Rydberg states, right? So you basically have, so like suppose you have two atoms in an S state, right? So this dipole-dipole interaction involves, for example, interaction between like, flip-flop, for example, an S and P or something like this, right? So, this process is not allowed. So you need to have dipole-dipole interaction. You need to basically flip-flop effectively to kind of to NP one atom and go, and another one should go to N-1, right? And so, and it's not a resonant process. Right? So basically what it means is that you need to do like a second order perturbation theory, because was correctly described. It's a square dipole-dipole interaction divided by this kind of detuning, by these energy differences. Right? So this gives rise to n to the power 8 over R6. That's still not allowed. So where does that come? Yeah, that comes from the detuning, right? And remember this Rydberg is 1 over n squared, and that is like a derivative with that cube. So that's where that's another. So that's where I love. Yeah, so if you look at the if you look at the real energy levels, the way it look like sort of like in a long distance, you have this kind of approximation, but then eventually when this shift becomes comparable to the nearby level, like this perturbation theory plays out. And eventually what happens here, you end up with this kind of spaghetti as well. Right. So basically, this is your initial state in a long distance. Right? Here you end up in this spaghetti. And actually what it really, really helping this whole R star that if you know what it is. So basically R star is a point where this kind of nice approximation breaks down. So basically what it really means, you cannot amplify two poles. So that's why definitely like the other blockade, but sort of larger than the R star. So that's the kind of.
Yeah. So when I was talking about T1, I was talking about the relaxation of the Rydberg state.
Yes. It's some kind of 100 microsecond.
Yeah, 100 microsecond. What is the biggest bottleneck of that? Is that black body radiation, spontaneous emission?
It's roughly I think they're both. I think it's about 200 microseconds.
Okay, 200.
It depends on n, but
Yeah.
they are roughly equal. I mean,
Yeah.
they're close.
And then the dephasing of the superposition state, is that like tens of milliseconds maybe, or
No, it's tens of microseconds.
tens of microseconds
It's
for both?
it's shorter than 2.
Oh,
right?
okay. Okay.
Then it's usually due to different types of things.
Okay.
Yeah, this, Rydberg states are not super long lived, right? So,
Thank
Yeah,
you. I
yeah.
appreciate it.